Hi guys, welcome to today's video. This is 2018 paper 1 question 6 and we're going to be doing some graphing the functions and also integration and also dealing with an inverse function, so let's get into it. So for this question, we're told that parts of the graphs of the functions hx is equal to x and k of x is equal to x cubed, where x is a real number as shown in this diagram. So obviously h of x is a straight line and h of x cubed will be a nice cubic function with sort of a flat bit in the middle. And for part A, we're told to find the coordinates of the points of intersection of the graphs of the two functions. So really, when you're dealing with coordinates and points of intersection, usually there's going to be two different functions equal to one another. So in other words, where h of x is equal to k of x, graphs intersect. So that's kind of a easy rule you can just know for these. So in this particular question, we know that x cubed is equal to x at the points of intersection. So I'm sure many of you will probably already know this only makes sense for one number, and possibly two numbers, and they're very small numbers. In fact, one of them is just 0. So that kind of gives it away, but there is actually a very correct way to do this and a sort of shortcut way to do this. So we're going to show you both of them. So, you know, a shortcut way to do this that's not technically correct, but I'm sure many people do it this way, is just by dividing across by x, and x squared equal to 1. And therefore, you know, whatever number squared is equal to 1 is where the graphs might intersect. So, you know, you could just say that x is equal to 1 and x is equal to minus 1. So, you know, this seems like a logically sound argument and, you know, there seems to be no problem with this. But really the problem arises when this doesn't account for the existence of x is equal to 0 as a solution as well. So, you'd also have to spot that. And, you know, if you have knowledge of cubics, you'd know that there should be 3 solutions maybe. So, you know, it's not to say you wouldn't spot that as well. But actually another problem is that when we're given x squared is equal to 1, we actually need to know what x is in every case. So we don't let x be plus or minus 1. We just always assume that when x squared is equal to 1, we're only dealing with 1. So we're not dealing with minus 1 at all. So that obviously complicates this problem, makes it sort of, you know, mathematically inaccurate to do it this way. So if we just go back and we rewrite this problem as x cubed minus x is equal to 0, we actually just try and factorize this as you would a quadratic. We can see that x squared minus 1 all times x is also equal to 0. And furthermore, we can separate this out because this is the difference of two squares, which will always be factorized in this way. So x minus 1 times x plus 1. And that's something you should just learn off because it does come up quite often. But it's pretty simple, just the square root of the first number minus the square root of the second number, all multiplied by the square root of the first number plus the square root of the second number. So, but back to the problem now, we've got 3 different factors, which we have equal to 0, and therefore we've got 3 solutions. So our first solution is x is equal to 1 as expected, our second is x is equal to minus 1, and our third is x is equal to 0. So in this way, we found all 3 solutions, and at no point have we avoided the argument or, you know, cheated it in any way. So this is the way you should always do these type of questions. So those are our 3 x values, but we're actually not quite done because it asks us for the coordinates, not just the x values or the x coordinates. So, you know, this is a very, very simple version of a problem like this. So because we're dealing with the function h of x is equal to x, our coordinates are just going to be equal to, you know, the same thing twice. So 1, 1, minus 1, minus 1, and 0, 0. So it's just good to put that down because that is exactly what they ask for. So not a bad start to the question. Quite easy, you know, for most people who can do a bit of factorization. So quite handy and it's worth 10 marks. And part B asks us to find the total area enclosed between the 2 graphs of the functions. So in other words, what we're looking for is this area as well as this area down here. So, you know, both sides of the y-axis. So if we just get rid of these 2 lines for a second. So basically what we're trying to find here is everything that's below the function h of x, which is this straight line here. So we'll just draw a line down from where h of x and k of x cross. So we're trying to find all of this area in here, in this blue triangle, minus what's below k of x, which is this curve here. So minus everything in this now purple triangle, which is all below k of x. Although it's not really a triangle, but you get the idea. And what we're going to be left with is some value for the area of what this segment here that we haven't colored in pink is. So now we've discovered the area we're trying to find. But one problem we will run into when we're integrating is this will actually be treated down here as a negative area. So that part will actually cancel out our other area, and that's obviously not what we want. But it's pretty clear to see that this is symmetrical, or the two portions of the area we're looking to find are equal. And there's no need to prove that. We can just assume that because it's pretty obvious. So we can just take that for granted. And what we're going to do is we're going to integrate the area of x minus x cubed, but we're going to multiply that by 2 to account for this area down here. So therefore the area we're looking for is the area under h of x minus the area under k of x, all multiplied by 2, as we discussed when we're looking at the graph. So that's 2 times the integral of x minus x cubed dx, but we also need to identify our limits. So we're going to be integrating from minus 1, which is the point of intersection over here, which we found in part A, to 0, which is this point. So in order to find what we're looking for, we're going to be integrating from 0 to the point of intersection, which we've established in part A is 1. So we're integrating from 0 to 1. And important to remember that the leftmost limit that you're dealing with in integration will always go on the bottom of the integral, so that's important too. And it may change the answer in some cases. So because we're integrating a polynomial of x, our rule is up here at the top of the table. I'm sure many of you know it off by heart, as you probably should, but in case you do forget it, it is in your all tables here on page 15. So we're just going to tuck our rule up there into the top right corner, and we apply this rule to x. So our power is 1, so we're just going to increase that by 2 and put it over 2 as well. And do the same thing for x cubed. So increasing our power to 4 and then put it over 4, and that's from the limits from 0 to 1. Okay, so now we're just going to sub in 1. So that will give us 2 times 1 squared over 2 minus 1 to the power of 4 over 4. And you don't have to include 0 in that because you're just going to get 0 over 2 minus 0 over 4. But just keep in mind as well that if you were to integrate, let's say, a trigonometric function like sine, you would definitely keep this in because some values of sine 0 actually do have either positive or negative values. So you need to keep that in mind. So therefore we have 2 times a half minus a quarter, which is 2 times a quarter, which is equal to a half. And we need to make sure to put in the units squared as well because we're dealing with area. And that's it for part B, part 1, once you find that area, and it's worth 10 marks. So finally, on the diagram of the previous page, using symmetry or otherwise, we've got to draw the graph of the inverse of k, which obviously is the inverse function of k. So they do kind of drop a hint that you can use symmetry, but just to show you how you do this regardless of whether symmetry works or not, we can say that k of x is equal to y, which is equal to x cubed. And we're just going to quickly write down 2 steps, which is first to isolate x, and I'll explain the second step in a minute, but first of all we're just going to isolate x. So x is equal to the cube root of y. Now for our second step, we're going to let x be the inverse function of k, so we're going to rename x. And we're also going to rename y, just to replace that with x. So that's kind of the 2 steps involved in this. So therefore the k inverse of x is equal to x to the power of a third. Now in this case, we can use a calculator if you want, but it's going to be resulting in the same thing. But in this particular example, it just so happens that what we get is actually the image of k of x across the h of x as an axis. So our function of k inverse of x actually ends up looking like this. That's just nice and convenient, but it won't always be symmetrical like this, so don't expect it to be. But that's our graph of k inverse of x. And that's actually for this question. The part 2 there is worth 5 marks for drawing the graph. So however you manage to do that, that's worth 5 marks. And I hope you enjoyed the video. If you did, there's going to be other similar videos in the description, as well as other useful resources, if you're struggling a bit. And I'll see you next time.